Okay, so I want to do some examples dealing with rational functions. So I want to do this section on vertical asymptotes and holes. So vertical asymptotes and holes, it's kind of related to domain issues, okay? Places where the function is not defined. So they have to do with the denominator, right? So you look at the denominator, and like on number 1, you have an x minus 7 down there. So x minus 7 would equal 0 if x were 7. So you know you don't want x to be 7. And then notice that that's not an easily fixable problem because there's not a factor of x minus 7 on top. So this right here is going to be a vertical asymptote. Vertical asymptote at x equals 7. Okay. Now on number 2, the denominator is 5x minus 9. It doesn't matter what's in the numerator except for checking to see if you can cancel out a common factor. But there's nothing common top and bottom. You find out what causes 5x minus 9 to equal 0. In other words, you just solve that for x. And this is your vertical asymptote. Okay. Now here we need to really rewrite this. The numerator is factored into x minus 9 times x plus 3. But see, we can factor the denominator of that into x minus 3 times x plus 3. All right, so the domain would be all x's except an x of 3 or an x of negative 3. Okay, but look at this. See how down here x of 3 and x of negative 3 are the places where the function's undefined? Well, do you see how the x plus 3 can be canceled out? Okay, so it's a fixable problem. So that means the x equal negative 3, the number associated with the factor x plus 3, that right there is going to produce a hole. You're going to have a hole at negative 3 and then wherever h of negative 3 turns out to be. Okay, that would be a hole. All right, on the other one, that's an equals. It's just my pen has an issue. At the other factor, an x of positive 3 would make it be 0. It's not something you can cancel out, so that one is going to lead to a vertical asymptote at 3. Okay. All right, now look at number 4. You have an x minus 8 on top, x minus 5, x plus 9 on the bottom. There's nothing common. You're not going to have any holes. You're going to have a vertical asymptote at x equal 5, and you're going to have one at x equal negative 9 as well. Okay, vertical asymptotes at both of those. Okay. All right, now this is an interesting one. Okay, x squared plus 9. Let's think about that. No matter what you plug in for x, you're squaring it. So 0 would be 0 when you square it. If you put a positive 3 in, you'd get positive 9. If you put a negative 3 in, you'd also get positive 9. This right here can never be 0. Never is 0. So you don't have any holes. You don't have any vertical asymptotes because this is never equal to 0, so you never have a problem. The domain is all reals. Okay, so you don't have any trouble spots. So you don't have any holes, no holes. Gosh, this isn't right. You have no holes, and you have no vertical asymptotes either on this one. Okay? All right, let me go back to my original worksheet, take another snip. So let's do the oblique and the horizontal asymptotes this time. Get it as far up as I can. Okay. All right, so to find horizontal asymptotes have to do with end behavior. What does the function ultimately do in the long run? Okay, and then you've got those rules about when your denominator is bigger, when the numerator and denominator have the same degree, and when the degree on top is bigger. Okay, so the degree of a polynomial is basically the biggest exponent you see. So the degree on number 6 on top is 2, and it's the same on the bottom. So you're going to have a horizontal asymptote, and it's going to equal the coefficients of the leading terms. So this is going to be it. Now it's a horizontal asymptote, so it's y equals something. It'll be y equal 1. Okay, later, that'll have to do with the limit as we let x go towards positive infinity. Okay, or if we let x go towards negative infinity, the limit's going to be 1. Okay, now let's look at 7. All right, so on this one, you see on top, we have a degree of 2. On the bottom, we have a degree of 1. So on top, degree is 1 more on top. 1 more on the top. That means you're going to have a slant asymptote. Okay, so this right here, you might not remember at all how to do. Let me erase this part. So this is when you would do division. You could either do long division like this, okay, and take care of the problem that way, or you could use synthetic division. And back in pre-cal, you were kind of fresh on synthetic. We could use synthetic because we were dividing by a linear factor. So what you would put in the box is the number 3, and then we would take the 1, the 8, and the negative 3, the coefficients in the numerator, and then we would do our synthetic division. Okay. And then what we know is that 30 would be the remainder. This right here would give you an x plus 11. Okay. And so your slant asymptote would be y equals that, x plus 11. This is your quotient, is what you get right there. Like if I did the long division, I'd wind up with the x plus 11 at some point up there on top. That's the quotient. And so this one, the answer would be that you have a slant asymptote. It would be y equals x plus 11. Here you have a horizontal asymptote at y equal 1. Notice they're all y equal type things. All right, now on number 8, the degree on the bottom is bigger. Okay, so that's an easy one. You're going to have a horizontal asymptote right there at the x-axis. Y equals 0 is really the x-axis. And then this one's just kind of out of order, but you see how the top one is really a negative 3x plus 4, the bottom one a negative 2x plus 3. The degree is the same. Then you're going to have a horizontal asymptote at y equal positive 3/2. Okay. All right, so really back here on number 7, when you're doing that problem back on number 7, and it says find the horizontal asymptote if there is one, you would say there's not a horizontal asymptote. It's a slant asymptote. And then that's the way you would work it out. Okay. On 10, it's asking us to find those slant asymptotes. So let me do this a little more thoroughly. So if you took the x minus 8 and divided it into x squared plus 6x minus 7 using long division, you could do that. X would go x into x squared x times. Then you multiply back, it'd be x squared minus 8x. Okay, let me change colors because this is the tricky part. Then you have to subtract, so I like to go in and change the signs. And then I'd wind up with 14x minus 7. Then I would do again, x into the 14x this time, would go 14 times. Multiply back, I'd get 14x minus, that's 112, right? 32, yeah, 112. All right, then I'm ready to do my subtraction, so let me change my signs. I like to subtract by adding the opposite, so I'm going to change my signs and add straight down, and I'm going to wind up with 105 positive. Okay, the remainder doesn't really matter. This is the quotient. Your oblique asymptote would be y equals x plus 14. Okay. Now, let me do that same problem using synthetic division in case you're, since the denominator, since what you're dividing by was linear, you could have put 8 in the box and then put the 1, the 6, the -7. Okay. And then use synthetic division. Okay. Oops. It's not 132. It's 80 and 32. I'm just double checking. And that would be 112. And then take away the 7, you'd get 105. And then you have to know how to interpret this. So this would be your constant. This would be your variable. So that would be x plus 1x plus 14. And that's your quotient. And so that would be y equals x plus 14. All right, so let's suppose you're trying to do this one using synthetic division. X plus 6 corresponds to the number -6. I'm going to put -6 in the box. And then I'm going to write down the coefficients of the polynomial on top. Do my synthetic division. So you bring down the 1, multiply, add straight down, then multiply. -6 times -9, that's positive 54. Add straight down, you get a 61. That's the remainder. This is the quotient, and that would give you your oblique asymptote, y equals x minus 9. Okay, so if we did the limit of these two functions, it doesn't wind up approaching infinity. Okay, well, it depends, I guess, on what number you wind up using, but okay. As x goes to infinity, okay, you've got this function approaches actually y equal x plus 14. Okay. All right, let me go back to the homework. I don't like my videos to get too long, so I may stop this one and then do all the graphing together. So I think I will.